Thank you so much for the introduction, Professor Borisov. So my name is Emir Gürsoy, and I'm a PhD student from Georgia Institute of Technology. And today I will be presenting our work titled Utility-Aware Synthesis of Differentially Private and Attack-Resilient Location Traces. This is joint work with my advisor, Professor Ling Liu, as well as my lab mates Stacy, Lee, and Wenqi. So as you can imagine, a lot of companies can easily, with the emerging popularity of location-based devices and GPS-enabled mobile devices, a lot of companies can easily collect large volumes of location trace and trajectory data. There is great value in analyzing this data, both from governance perspective and commercial perspective. So for example, from a governance perspective, it can help benefit urban planning, population growth control, as well as analyzing, for example, at what times throughout the day certain roads will be congested. Also, from a commercial perspective, it can help benefit companies to produce better location-based advertisement, spatial hotspot discovery, as well as analyze, if you're a company like a taxi company or an Uber, you say you want to analyze the passenger demand at different times throughout the day, it could also be beneficial for you. However, typically, the trajectory analytics is not done only by the party that is collecting the data. The data collector often needs to share this data with other parties to facilitate the data analytics. So the data may have to be shared with machine learning as a service providers, such as these guys. It needs to be shared, for example, with city officials and policymakers. It could have to be shared with university researchers, such as myself, or it might have to be shared with the general public, as in the case of NYC Taxi and Limousine Commission's release of anonymized trip logs and Uber Movement. However, the sharing of location trace data is obviously raising legitimate privacy concerns because location traces are sensitive by nature. So unauthorized disclosure of these location traces can lead to intrusions of personal privacy as well as intrusions of organizational privacy, such as disclosure of people's home locations, work locations, whether they visit they frequently visit certain religious places, health clinics, hospitals, and so on and so forth. And this is not just like a story that we're making up. Actually, with the NYC Taxi and Limousine Commission's release of so-called anonymized trip logs, some researchers assumed the role of an adversary and asked the question, what can I learn from this data? And it turns out that they were able to stalk celebrities. For example, they could find out where Bradley Cooper and Jessica Alba were going in New York City, even though these people were apparently trying to run away from paparazzis. And also they could figure out, for example, the home addresses of people visiting the Gentleman's Club. So of course, these are really bad things. We don't want these things to happen. So what's the goal of our work? The goal of our work is to stop such inferences from happening. And to put it a little bit more formally, the goal of our work is to enable the sharing of privacy-preserving trajectories with high utility. So what we mean by this is that we have to satisfy certain privacy constraints, as well as privacy. After the privacy constraints are applied, our final trajectories should still be realistic and still be useful for various geodata analysis and machine learning tasks. So the technique we use to achieve this goal is what we call trajectory synthesis using generative models. So what we do here is that given a certain set of real trajectories that were collected from actual individuals, we train what we call a generative model, which is able to synthesize new trajectories, synthesized trajectories. And within this generative model and the synthesized trajectories, we ensure that we add some utility constraints and privacy constraints so that the final trajectories that will be released to the public or be given to a third-party researcher will satisfy our utility and privacy goals. So we designed a system that we call AdaTrace to achieve this goal. So what AdaTrace does is, given a set of actual location traces, it uses feature extraction techniques to learn what we call a private synopsis. So the private synopsis is where we capture various types of pertinent statistical information from the actual traces. And this private synopsis is perturbed with a controlled amount of noise to satisfy both differential privacy and attack resilience. After the perturbation is complete, we use what we call a synthesis algorithm. So what the synthesis algorithm does is it combines the perturbed features to create generate some synthetic traces that are sanitized. So let us first try to clarify what we mean by the use of differential privacy. So basically, in the rest of the presentation, I will talk about the three aspects of our system. The first one is differential privacy, the second one is attack resilience, and the third one is utility preservation. So let me start with differential privacy and try to clarify what we mean by the use of differential privacy in a system like this. So let's say that we have this toy data set D consisting of 4 individuals and their trajectories. Let's say we feed this data set to a randomized generative model. For example, AdaTrace itself is also a randomized generative model. And the output of this, with certain probability, the output will be some generated synthetic trajectories. Of course, with some other probability, some other output may occur, since our generative model is randomized and probabilistic. Let's say for now that we remove one of the individuals in dataset D and we create a dataset D prime. So in this example, we removed Carol's trajectory from my dataset and we entered Aaron's trajectory to the dataset. It could be someone else. So we call such a dataset D prime a neighboring dataset of D, since it differs from the original dataset by one individual's trajectory. Say that we feed this dataset D prime to the randomized generative model, and then with a certain probability, the same outcome can be observed. So what differential privacy says is that the odds ratio between these two probabilities should be less than or equal to e to the power epsilon. So what this means from an adversarial point of view who only has access to the generated synthetic traces is that after the adversary observes the synthetic traces, he will not be to reverse engineer, he will not be able to figure out whether those traces came from dataset D or whether they came from dataset D prime. So it gives some sort of membership privacy to Carol, Aaron, or it could be anyone else in the dataset. So one thing I would like to also mention here is that this is a trajectory level privacy guarantee. So essentially we're trying to hide Carol and her whole trajectory, not just like one instantaneous location point. And this is how this kind of work differs from the differential location privacy work. This kind of trajectory level membership privacy guarantee is relevant against various types of recent attacks that were discovered in the literature. One of the most popular one, I think, is the membership inference attacks. So there was a paper in NDSS this year, and then there was an SMP paper last year showing the possibility of membership inference attacks on both location aggregates and machine learning models. So what we propose in this work is if instead of training the machine learning model on the actual data set, if we train the machine learning model or compute the aggregates on the synthetic traces which already have the membership privacy guarantee, the aggregates or the machine learning models will inherit the membership privacy guarantee, and therefore these kinds of attacks can be circumvented. And if the utility constraints are also satisfied, while these attacks are prevented, the generated synthetic traces or the machine learning models will also be useful in various tasks. So I've talked a little bit about the differential privacy aspect of AdaTrace. I will now talk a little bit about the attack resilience aspects of AdaTrace. And the reason that we want to incorporate attack resilience is because we see there are lots of attacks that are possible in the location privacy domain that are not typically covered, that fall outside the scope of coverage that is provided by differential privacy. So I will very briefly give an overview of the 3 types of attacks that we consider in this work. The first attack is the Bayesian inference attack. So basically in differential privacy, we don't have an idea of like this zone in our map is sensitive, this zone is like not as sensitive. So we would like to incorporate that kind of idea into our framework. So what we say here is that there will be certain zones such as a school zone or a hospital that we call a privacy sensitive zone. So for those privacy sensitive zones only, we say that the adversary has a prior belief. For example, this could be the hospital publishing certain annual statistics about how many people visiting the hospital are coming from midtown, downtown, etc. And after obtaining a copy of these synthesized trajectories, the adversary is going to formulate a posterior belief about the people visiting the hospital. So for the sensitive zones, what we would like to ensure is that the information that is learned from the synthetic trajectories is not too much. But we do so by limiting the distance between the adversary's prior belief and the posterior belief to be less than a threshold theta. The second type of attack that we consider is a partial sniffing attack. So as you might imagine, if you go to, let's say you're a Yelp user or you're a Foursquare user, for example, let's say you strike up your phone and then you say, okay, at 4 p.m. I was at this restaurant, at 5 p.m. I was at the coffee shop, at 6 p.m. I'm at the gym, so on and so forth. So basically this is you giving away a sub-trajectory of your full trajectory. But maybe after you hit the gym, you go home, but you don't share your location from your home because you don't want that third party or an adversary to know where your home is located. So in that case, the goal of the adversary is armed with your sub-trajectory information. The goal of the adversary is to figure out your full trajectory. So they want to learn where your home is located. So we would like to, so the idea that we use to stop such inferences from happening is that we actually limit the amount of intersection between the actual user's trajectory and the linked synthetic trajectory to be very small outside the sniffed part. And then the third attack that we have is the outlier leakage attack. And in this case, we observe that certain trajectories in our universe can be outliers because they are unique in one or several ways. So what we mean by this is, for example, there can be certain trips, like Uber trips from downtown to midtown for $10. And there would be hundreds of those trajectories every day. However, if you have, for example, if I live in a rural area, if I own like a very large farmhouse in a rural area, and then I make a trip to the airport and I pay $125, and this trip is at 4 a.m. at night, that tells an adversary that, you know, I'll be traveling and this will be like inviting burglars to my apartment. So these kinds of trajectories are the ones that actually have to be protected a lot more. So we, in this case, we use a defense that is a form of a crowd blending privacy. You can think of this as similar to k-anonymity, for example. We say that an output trajectory should blend in a crowd of k trajectories, and the discrepancy between the trajectories within this crowd should be less than a threshold. So we have to have a large crowd. So for example, we have to have, if for the farmhouse example, let's say we have multiple other trajectories that are starting from my farmhouse going to other places in town, not just the hospital, and we have maybe 5 trajectories starting at various places in the city and coming to my home. So this would prevent the adversary from inferring that my house is going to be empty for the next 1 or 2 days. So I've talked about the differential privacy aspect, and I've talked about the attack resilience aspect. Now I will talk a little bit about the utility aspect of AdaTrace with the help of our experimental results. So in our experiment, the whole experiment is based on the idea of comparing the real trajectories that we have versus the synthetic trajectories that are generated at the end of our system. And we would like to learn how well are the aggregate features of the data being preserved. And the reason we do this comparison this way is because as long as we satisfy certain privacy constraints in terms of differential privacy and attack resilience, we would like to keep utility as high as possible. So satisfying the privacy goals with as much utility as possible is preferable. We compare our system against 3 existing works. Those are Ngram, DPT, and SGLT. We use 7 metrics, experimental metrics in our comparison, and 3 datasets. So on this slide, I just include like a very large table summarizing all of our results. We actually, I included this to be like a highlight of all of our results. In the paper, we go into detail explaining each of these utility metrics one by one. Why do we observe these kinds of traits? But then as a really like a 10-kilometer highlight, we would like to say that out of the 63 comparisons we have, AdaTrace outperforms the previous works in 53 of those comparisons. And when it does outperform the existing works, it's often by 2 to 3-fold improvement in utility. In addition to our numeric experimentation and computation, we also did some spatial and visual comparison between the actual traces and the trajectory and the traces that are generated by various generators. So on the left-hand side, you see the actual density distribution, spatial density distribution of the Brinkhoff dataset, and on the right, you see the visual densities generated by various generators such as DPT, SGLT, Ngram, and AdaTrace. And you can see that AdaTrace is good at keeping the relative spatial density of the trajectories rather well. Another point that, Another point that I would like to make is AdaTrace is also computationally more efficient. According to our execution time measurements, on the Brinkhoff dataset, which consists of 50,000 trajectories, AdaTrace can complete in less than 3 minutes, which gives us, which shows that AdaTrace is efficient, effective, scalable, and it can be used on larger real-world datasets that are collected by various companies. I would also like to talk a little bit about the. Okay. I'd also like to talk about the attack resilience properties and how the privacy parameters in the attack resilience part impacts trajectory utility. So the first attack that we had was the Bayesian Inference attack. So the most relevant parameter here is obviously the privacy parameter theta. So if you look at the bottom left graph, as we increase the privacy parameter theta, we allow the distance between the priors and the posteriors to be large. So what this means is effectively we're allowing the adversary to learn more about that sensitive zone from the synthetic traces. So that means AdaTrace is allowed to inject more and more utility to the synthetic trajectories that are being generated. And as a result, we see on the bottom left graph that as we increase the parameter theta, there's a utility improvement. Also, there's an implicit parameter here, which is the size of the sensitive zone Z. So you might say, for example, okay, I'll just say my whole, the whole universe is a sensitive zone, and I would like to protect everything, or I would like to rely, I set everything as the sensitive zone, and I rely on, for example, differential privacy to protect everything. But then setting the whole universe as your sensitive zone is not actually a very good idea, because as you see from the graph on the right, as we increase the size of our sensitive zone, we also see an increase, a superlinear increase in terms of the amount of error that is introduced in the trajectories. So that means you're welcome to use sensitive zones. However, if you would like to limit an adversarial knowledge in those sensitive zones, keep them as small as possible, as reasonable, so that at least from the synthetic trajectories you get some utility out of them. The second attack we had was the partial sniffing attack, and the relevant parameter here is the parameter phi. So we experiment on the impact of parameter phi versus the amount of error on different data sets. And an interesting, maybe a little counterintuitive result that we find is that even though we make parameter phi more relaxed or more strict, we don't see an exact influence on that on the amount of error. And this can be actually attributed with the way that AdaTrace is implementing the defense to the partial sniffing attack. So conceptually, in a very simple sense, what AdaTrace is doing is essentially it's taking, so let's say my trajectory was sniffed, and let's say that my friend's trajectory is sniffed. So what AdaTrace does is it cuts the part that is not sniffed, and from my trajectory, it cuts the part from my friend's trajectory, which is not sniffed, and it kind of garbles them among one another. So what this achieves is basically my individual mobility is not being preserved, my friend's individual mobility is not being preserved, but if we measure the aggregate error, the aggregate spatial error, then we don't see a change in the amount of utility that we get. And the final attack we had was the outlier leakage attack. And the two relevant parameters here are the crowd size k, similar to k and k anonymity, and the maximum distance parameter beta. So as we increase the parameter k, that means we want to build a larger crowd of similar looking trajectories. However, if we try to do so, as you can see from the graph, there will be a lot more trajectories that are labeled as candidate outlier trajectories. Also, this is analogous, for example, in k anonymity, that if you want to increase your k in k anonymity, then you have to pay higher utility price typically. Also, you can see the impact of the parameter beta, the maximum distance or variance parameter. So if you set beta to be very, very small, then you have a lot of trajectories that will be labeled as outliers to fail the defense. So the very small beta could, for example, could be I want 100 trajectories from downtown to go to like terminal 1 at the airport. If I relax beta a little bit, I say I have 100 trajectories from downtown, but they have to go to the airport, but they can go to any terminal. If I do beta even more relaxed, I can say I want those 100 trajectories to go somewhere near the airport, but it doesn't have to be the airport, for example. So you see that the impact of that, as we relax the parameter beta, we have less and less trajectories that are being labeled as outliers. So in conclusion, the idea of our work was that generative models are useful for privacy-preserving and utility-preserving trajectory synthesis. And we developed a system that we call AdaTrace with 3 simultaneous goals to show that our claim works. The 3 goals that we have was differential privacy, attack resilience, and utility preservation. And we showed via experiments that AdaTrace offers improved computational efficiency as well as privacy and trajectory utility compared to existing works. So thank you very much for your attention. And if there's time, I'll take questions. Please come to the mic. It's a lot of questions.
So you discussed
Yes.
the other parameter, how they affect utility, but I didn't see what's the parameter you use for epsilon for the differential privacy.
Yes, sorry about that. So that epsilon is actually in this graph. So you can see the epsilons we use on the left is epsilon 0.5 to 2.0.
Hi. So my question is related to the attack resilience part.
Yes.
You did multiple experiments based on what kind of attack it is. How does AdaTrace know? Like, how does it realize what kind of attack it is? Do you have to manually input all the parameters?
So yes. So how we think of this is, for example, the user gives us the real set of traces. So if we consider this slide, for example, the inputs to AdaTrace is the actual traces, the collected traces, and then a bunch of privacy parameters, the epsilon parameter for differential privacy and the attack resilience parameters for each of the attacks. So after the user specifies these parameters, it's the internal working of AdaTrace. And by the time AdaTrace says, I'm done, I've generated all the trajectories that's done, all of the attacks and the differential privacy constraints will be satisfied. So basically, to answer your question, yes, we do take them as inputs.
Okay, so it's like a semi-black box feature.
Yes. So for the end user, you could treat this as a black box. Yes.
Thank you.
Sure.
Are you familiar with the impossibility result of Dwork and Neural from 2008?
What does that result say?
I thought it said that you couldn't prevent the kind of Bayesian inference attacks you're saying you're preventing.
Well, so it depends on the privacy parameter, right? So you could set the parameter to be a little bit more relaxed and then prevent it on top of, the guarantee that you get on differential privacy. It could be a little bit more relaxed from the, I don't see why I would never be able to prevent Bayesian inference because it's just yeah, go ahead.
Well, so how is your prior beliefs be quantified over? It's because the set of possible prior beliefs are so large, you can always find some pathological adversary that learns exactly what it needs to know now with certainty that you visited, say, the hospital.
I see. That makes a lot of sense. So yes, for an adversary that has a lot of information, for an adversary that has super prior beliefs, then yes, satisfying a defense like this can be very difficult. Whereas if you have an adversary that is only bounded, for example, by the example I gave was like the annual statistics that are published by the hospital. So that's like a weaker adversarial knowledge than, for example, having access to Uber's trip data. So in that case, it's becoming more possible to satisfy this kind of defense. Also, it could be an uninformed adversary, for example, saying I have a uniform distribution of prior beliefs. In that case, it's usually the easiest to satisfy this kind of defense.
Okay, so you have some kind of implicit constraints on B. Okay.
Yes, sure, yes.
I was going to say, it seemed like some of the attacks you consider are already prevented by differential privacy, in particular the outlier leakage. I mean, that's exactly what differential privacy should prevent. And I looked quickly at your paper, and you just have a sentence that didn't make sense to me. But can you say why it's not implied by differential privacy? Are you assuming something about the input?
So not really, but like if you consider differential privacy, the amount of noise, so if you want to, let's say that you have to account for all of the cases, all of the types of outliers that are in the data. So you can say
it's swapping the outlier for a regular sample, right? That's exactly what differential privacy would prevent.
Yes, but then it's not as clear as this in the case of data synthesis, right? Because the mapping is not just like one-to-one. You can't just take an input data and just like modify it a little bit. That's what differential location privacy does, but it doesn't prevent the kind of membership privacy that we're kind of working on. So then it's not like you take an input data, you change it, and then you produce the output. It's more like I have to statistically test from the output that I generate, how does it relate to the other outputs and how does it relate to the input?
Okay, I guess it's not clear, but we can discuss later.
We can discuss outside, sure.
Great.
Yes.
Can the next speaker shut up during those last questions?
Okay. So you are using differential privacy, but it seems that two of your defense look at the data. So I was wondering if this could really, because you use them to select some of their trajectories, so this could reveal some information. So maybe you will lose some of the guarantee of differential privacy.
Yes, that's something that we actually thought about, and you're right in that sense. But so the assumption here is that the things that are, for example, the Bayesian inference attack, the priors are something that is given also to the system. So we don't actually have to look at to the data to figure out the priors. For example, for the partial sniffing attack, we would also assume that, for example, the sniffed parts will be provided to us as input. So we don't have to go and test, look at the actual data to get the sniffed parts as well. So those are the things that we assume would be given to us as inputs, saying that, okay, there's a sniff region here, there's a surveillance camera. People generally, tell us from 3 p.m. to 6 p.m. where they go. And so those are the things that we sniff. So we don't actually have to go and figure that out from the real data.
Okay.
All right, we're going to have to stop here, but hopefully Emmer will be available after the talk to answer some more questions. Let's thank him one more time.
All right, thank you.